Hi, this is Professor Clay. Section 16-2, I'm going to talk about static RAMs. Large-scale random access memory, RAM, also known as read-write memory, is used for temporary storage of data and program instructions in microprocessor-based systems. The term random access means that the user can access, by reading or writing, data at any location within the entire memory device randomly without having to sequentially read through several data values until positioned at the desired memory location. An example of a sequential non-random memory device is magnetic tape, where you had to actually spin through the entire tape to get to the end or back to the beginning. A CD or hard disk drive has random access capability. So we'll just take baby steps right now, but we'll start out with a RAM. This is rather small, but you really have to start out with a smaller one before you can understand the practical, the high mega and the giga type RAMs that we have available in processors today. But the 2164 is a rather old static RAM, but it's really nice because it's very understandable right down to the bit level. So let's take a look at it. It's a static RAM. It uses MOS technology. It's set up with 4096, which is abbreviated 4K, and 1K is defined as 1024, which is really 2 to the 10th power, which is 1024. Of course, we're going to be 2 to the 12th power to get 4K. Okay, so memory locations. Now that's how many memory locations there are, with each location containing a single bit. So this is a bitwise sort of a memory situation, just to help us understand how these work. It's written as 4096 by 1. This is very small by today's standards, but by studying this operation, it's a good start for understanding the larger SRAMs. So let's start out by looking at the logic symbol. As you can see, it's got address A0 through A11. That's 12 address lines. If you take 2 to the 12th power, that's 4096 possible different combinations. So there's more than 4,000 different locations inside this chip. Each location has one D out and one possible D in. This is the same memory cell. We're either going to be writing into the cell or reading out from it. Now we've got a WE command, and if you read that, that's called the write enable. When that goes low, we're writing to the chip, which means we're sending data into the chip. So when you make that line low, the chip select, of course, has got to be low just to make the chip work in the first place. Now, when you look at the block diagram, here is the memory array. It's set up as a 64 row by 64 column array. That gives us, if you multiply those numbers, you'll get the 4096. So we take the address lines and we'll take the A0 through A5, which is 6 address lines, and we'll use that to set up the row that we're going to select, the row, and then we'll take the A6 through A11, the remainder, and use that to select the column. And by specifying the row column, we'll pinpoint an exact memory location inside this array. Now the data in. The data in will come in if we have a high on this enable on this buffer, and we get that high from an AND, which is looking for a low and a low. Well, if you're doing a chip select and you got a low WE, then we're doing a write command, and that's why this is enabled, and the data will pass in to the column I input output circuits. Now to get data to come out of this, we have to have a high on this enable line of this inverting buffer, and that high comes from here, which says we have to have a low CS and a high WE, which means we're doing a read operation. And if you're doing a read, you're pulling data out of the memory cell. Now in figure 16.5, I give you a lot more detail on selecting the row columns. This is a 2147 4K by 1 static RAM, and we're looking at the address row and column decoders to select memory cell 1111 1 1. So the high order bits are all ones. We're going to place those on the A6 through A11. And then the low order 000010, we're putting those on the low order information, and there's that 1. Now this number right here decodes into the number 2, which is going to select row number 2. So row 0 goes across here, row 1, and then row 2. So we're selecting this row, and the cell within there is 111111, which is decoded into the number 63. If you did the binary on that, that's the 63. So the column goes up and down this way, and when you pinpoint the row column, there's the cell. So whatever's in that cell, that information is going to be either written to or read from. Okay, so figure 16-5C shows a functional diagram of a single cell within that static RAM. So this dashed line is a single data cell. We can bring data into it or pull data out. These are MOS transistors, or like they're FET, field effect transistors, and these are all N channel because the arrow's pointing in. Now, as soon as your bit select that came from your row column select is a high, this high is applied to Q3, Q4, which actually makes them a short circuit. So this cell is now connected to the outside world depending on which buffer is enabled. If this buffer is enabled, data is allowed to come in. So let's take a look at how you would write a 1 into this memory cell. First of all, to write, you'd have to make the chip select low and the write line low. This low comes out as a high that enables this buffer. Now let's place a 1 into this memory cell. If you put a 1 or a 5-volt level into this memory cell, it comes through, this transistor is a short, this 1 comes down and turns on Q6. When Q6 is turned on, it's essentially a short from ground to this point. This ground is fed back kind of like the cross NAND flip-flop that we looked at earlier in chapter 10, but this ground is fed back, which turns this transistor off, which essentially is like an open. Q1 and Q2 are just providing the bias necessary for their corresponding transistors. So with Q5 off, current will be allowed. And remember, this is a 1 here. This 1 is going to turn this on. VDD will be felt down on this transistor, and so that when you remove the data from the input by releasing the chip select or releasing the WE, this becomes an open, but we still have this bias current keeping this transistor on, which produces a 0, which turns this one off. So this cross connection here maintains that 1 in the memory cell by keeping Q6 turned on. Now when we want to read Q6, or the 1, we want to read it to the output, we take the chip select, keep it low, we make the WE high. That enables this line, which enables this buffer. Now the 1 that we put in here is actually going to be a 0 felt at this point. That's going to come out, and that's why we need an inverter at the D out, because remember, to put the 1 in, we actually turn Q6 on, so that 1 comes through, gets inverted in. I'm sorry, the 1 that came in turned this on, which pushed ground right here because it's a short, and the 0 comes through, gets inverted into a 1 again. So the D in that initially came in as a 1 is going to come out as a 1. So basically this is the functional operation of what takes place inside a single MOS cell. You got to multiply that by millions or even billions when you look at modern RAMs of today. In figure 16.6, I'm going to show you how the address bus is connected to the A0 through A11 line. So what you'll do is specify the address of the cell you want to look at, and we're trying to read the data out, so we have to make the not WE high to do that. So here's the timing for this. So you set up the address bus at this point, and then there's a length of time called TAA, address access, before the data before the data coming out is valid. Before that, the D at the output is either in high impedance state, meaning floating, or it's undetermined. So stay away from it. You can't read it until after you take care of the TAA nanoseconds and the TACS, which is the access from the chip select. Now here the chip select goes low. It takes a few, whatever the time is, nanoseconds or microseconds before the data is valid. So you have to look at the TAA and the TACS, and whichever one is longer, that's the length of time you got to wait before the data output is valid. Now after you raise the CS back high again, there's a THZ, which is the length of time it takes before the output goes back into its high impedance state so that you can do another operation. So the times are given in the bottom of figure 16-6. The TRC, which is the read cycle time, is 35 nanoseconds. That's the length of time from the beginning of your operation to the end of your operation. And then here's the TAA, 35 nanoseconds worst case max, and then TACS, 35 nano, and so on. So the chip deselect could be as low as 0, which means it's instantaneously high impedance, or it could be as bad as 30 nanoseconds. And the next figure shows when you're writing to it, you're going to be putting data in. So the write line is going to have to be pulsed low. Of course, the chip select's got to be low. And you're going to specify the address that you want to send the data into. So here's the timing waveforms for that. And remember, the data comes in on the low to high edge. So here's the edge that we're supplying. So what you got to do is make sure you got valid data available TDW nanoseconds before this low to high edge. And of course we're going to have the new address available. So you set up the address, you pulse the CS line, and when this goes low to high, it looks at the data input line and it pulls that data in and places it inside the memory cell. And the times are specified as in this table: 35 nano for the TWC, which is the write cycle time, and then 20 nanoseconds for the TDW, which is the data valid to end of write. That's really the setup time. That's the time you have to set the data, make sure the data is valid before you raise this high. And then the hold time, where you have to hold the data there after the edge, which is really 0, which means this line could be back at the beginning of this edge. So these times are real similar to what we looked at back in chapter 11 when we first started studying D flip-flop time considerations. Now, to turn this 1-bit system into an 8-bit system, we could have 8 of these 2147s and take the D in, D out line, tie them together, and bring it into the D0 off the data bus, and then take the next one into the D1 off the data bus, the next one into the D2, and so on, all the way up to D7, such that when you do the WE and the CS, you're accessing all 8 of these at the same time with the same address information. So they're all active. One cell in each one of these is active at the same time, so it dumps a whole byte down onto the data bus. When you look at circuit boards, you'll see them populated with many single bit RAM chips to make up a full byte. So practically speaking, we have, and I'll show you the table first, we've got a sample of some Hitachi low power static RAMs configured in different densities, a 4K bit, a 1 meg, a 4 meg, and so on. Now the 4 meg is configured as a 512K by 8. That means that there's 8 data bits at each of the 512K locations. So let's look at these different configurations. So in the case of the 6264, we've got A0 through A12. That's 2 to the 13th power, which is where you get the 8K from. 2 to the 13th is 8K. Each location, once you got the location, there's 8 bits located there. Okay, then the 62,256 is 0 through 14. That's 2 to the 15th power. That's where you get the 32K, and so on, and they get larger and larger, and they're even larger than that nowadays too. So it's up to you to look on the internet and search out some static RAM chips, and you can look at the latest configuration that's used inside your digital system. Now there's another type of RAM chip called the dynamic RAM, and these are the extremely large density chips that we use for our RAM inside our PCs. The difference is that they actually store their memory cells as a charged or discharged capacitor. So we'll look at that in the next section.